Utah, let's see, let's go here. Utah is higher than California, right? So when we jump, yep.
How is Utah's gravity lower than California? Because at higher altitude, and so it's closer to like.
Okay. So that would make it more gravity?
Because doesn't the sun like orbit like close you are in
Why? That's just what you heard somewhere? You're saying the closer, so if we have like the sun, the closer we are to the sun, the more gravity. So this has, so let's do A, B, C, D. You're saying D has more gravity than C. Isn't that just based on that? Well, what's gravity? First of all, what is gravity? An attractive force between what? Between what? What causes gravity? Well, what do we say causes gravity? That's really the better way to put it. What do we say what? The sun? It's mass that causes gravity. So any mass has a gravitational attraction. That's why we say it's a force of attraction. It's a force of attraction between two masses. We have to have two masses. So these two masses pull on each other. They want to come together. Okay? So there's a force of attraction between you and the earth. There's a force of attraction between you and the death. There's a force of attraction between you and everybody else in the room. Okay? So there's always this attractive force of gravity if we have mass. Okay? Yes?
I change my answer?
Sure, go ahead. You can go sit down. Okay? So that's what we need to look at. How do we calculate what the force of gravity is? Okay, and that's where we come up with, we have a law called Newton's Universal Law of Gravitation. And it says that the force of gravity, that's a subscript G, is equal to capital G. What is that? You remember that one? There you go. That's the gravitational constant. That's 6.67 times 10 to the negative 11th, right? That constant times M1 times M2, those are our two masses, divided by r squared. Okay? That's our formula for how we calculate that force that attracts those two masses. So it depends on what things. What changes, what can we change to change the force of gravity? According to that formula.
The axis or the radius.
What is the radius? That's the distance, right? So if I have two objects that are 1 centimeter apart and two objects that are 1 meter apart, which one's going to have the strongest force of gravity?
The meter. Or the centimeter.
The one that's closer, right? So this is what we're saying is, this is an inverse relationship. So as the radius goes up, as we get further and further apart, what happens to the force? It goes down, right? That's called an inverse relationship. So the further apart we go, and so if we're talking about the sun, we're actually talking about the force of gravity between the what? The sun and the earth, or the sun and a spaceship, or the sun and us if we're in a spaceship out there, or the sun and another planet, right? So the further away we go, the weaker that gravitational force between the sun and whatever it is we're talking about, the sun and the earth, is. So if we move the earth further away, there'd be less gravitational force.
Well, California's at a lower altitude.
Well, hold on, no, we're not going there yet. Let's go here, because what's the other thing we can change?
The masses of the...
The masses. So if I add mass to something, what did I do to the gravitational force? I made it bigger, right? That's where this is called the direct relationship. So if mass goes up, what happens to the force? It goes up too. What might you want to be doing right now?
Picking up.
Okie doke. Okay? So if mass goes up, force goes up. If radius goes up, force goes down. Right? That's the idea. So now let's go back to our Utah and California. Which one can I jump higher on?
She said
No, I got it. So, let's draw, let's not go back. Let's go to a new picture. And I'm gonna draw it this way. So here's Utah in the mountains, right? And here's California down on the beach, down at sea level, right? So which one am I going to be able to jump higher on? Which one has a stronger force of gravity? Now some of you mentioned, well, we have less air, right? Our air is not as thick. We're not counting any of that. All we're doing is talking about what happens to gravity, okay? So, what changes between these two? Yeah, the distance from? There you go, that's the trick. When we do this formula, if we're going to calculate like on a planet, we go from the center. So the distance, change color, from here to us in Utah, or from here to California, which one's bigger? Utah, right? So that would mean, so if R goes up, what happens to the force? It goes down, doesn't it? So that would mean that gravity's stronger where? In California, right?
Wait, so you could jump higher and Utah even?
Anything else change? Be careful. What else changes? Does the mass change? Does your mass change between California and Utah? No. Well, you could, but that's not mass, right? Mass is how much, like how many atoms you have in it. What you were talking about is weight, and that's because of gravity, right? So according to this, I would weigh more in California than I would in Utah. But does the mass change going to Utah?
No.
What's all this? That's a what? That's land. Isn't that the mountains? You gotta come up the mountains to get from California to Utah, right? So do we have more stuff underneath us?
Yes.
Absolutely. We have mountains of stuff underneath us, right? So yes, we have more mass in Utah. So what does that do to the gravity? The force goes up as well. So because we go further away, the force goes down. But because we also, to go further away, we add more stuff underneath us, the force goes up. Well, what was our formula? Right? So if I add, let's do this. Let's just say I double the mass. We're going to do one side where I double the mass. Right? And one side where I double the radius. Right?
Why? I'm trying to understand.
Well, we're saying we're changing one, right? We're gonna say we're gonna add more mass like we do in Utah,
okay.
and we're gonna add more grade just to see what happens. So this, we just pull that 2 out, don't we? I think I need my 1 and my 2. So that's 2g m1 m2 over r squared, right?
Yeah.
What happens over here? This is squared, isn't it? So what does that 2 do? Turns into a 4. So isn't that 1/4 g m1 m2 over r squared?
Oh, I see.
Do you see that? Because we take this, so this really becomes over 4r squared, right? Because we squared the 2, right? So this changes by 4 times, or is a 4th, and this changes by 2. So which one affects it the most? Is the mass affected the most? It's 2 times, this is 4 times.
Also, that's radius.
Does that make sense?
I thought it was 1/4.
It's 1/4 of what we had, where this is doubling, right? So this is a change by a factor of 4.
Yeah, so wouldn't doubling it increase it more?
Okay, now remember, we're not talking about which one increases it more. We just want to know which one's going to have the biggest effect. So if I change both of these, which one causes it to change the most?
Then the second.
The radius, because we have this squared, right? So a change in radius is an exponential change, where a change in mass is a linear change. We just multiply it by how many times we change it. So we'd actually have to do the calculation though, because we don't know what the mass is that we add because of the mountains, right? Because what really happens is we can have different densities in the mountains. We can have some mountains that actually are lighter than other mountains, so the gravity doesn't change as much. Or it may change more. Right? That's the trick. So right now, from what we've talked about, where would you say gravity is low? California or Utah? Which one's
What?
further? Even though we have more mass,
Oh, I
we
guess.
have more change because we're further, so probably
Utah.
Utah. Now the question is by how much? Could you measure a difference between California and Utah? If you could, where would everyone be playing basketball? Right here, right? Because you could jump higher here. We would never go to California. Or if you were doing the NFL Combine and you were trying to do vertical jump or whatever, you'd come here and have your vertical jump tested, right? So the change is tiny. Tiny, tiny, tiny. Because how many of you have ridden on an airplane? And how many of you have floated out of your seat because gravity was so? All of you, right? Yeah. Uh-huh. Nope, doesn't happen. Now, when you go on an airplane, what happens to gravity? When you go up in the airplane, does the gravitational pull go down or up?
It go down because you're farther away.
Because you're farther away. Did we add any mass underneath?
No.
No. And it's even higher than Utah, right? Utah's at like 5,000 feet. When you're in an airplane flying, you're up around 30,000 jet, right? So you're way higher, and yet you don't feel any gravitational change, right? That's the idea. It doesn't change that much in that distance. Gravity is a huge force. For us to feel gravity, do you feel gravitational pull between all the objects? Nope, you don't. If you did, we'd have a giant black hole at the top of the commons, right? Right there at the stairs where everybody stopped and everybody gets sucked in. Right? But gravity takes a huge mass for us to really be able to, tell. We can actually measure it. I've actually used a device in geology where I can measure the gravitational difference between a 10-foot rise in the floor of a building. I can measure how high the floor was raised based on how much gravity changed, how much that force of gravity changed. So we can measure some very sensitive changes in gravitational force. But you don't notice it. That's not a big enough change for you. And it's not like you take your scale, put it on an airplane, and you can read a difference on your scale. You will read more of a difference because you didn't get to take your drink with you. You got to drink for 4 hours. Right? Than you would because of gravity. Okay? Making sense?
So far.
Good question. Okay? Okay, so now let's look at what would that force be. Let's look at a calculation. Let's actually do a calculation. G, M1, M2 over R squared. That's our force of gravity. So what do you want to determine the force of gravity between? Do you want to do something small or do you want to do something big?
Small.
Small? You want to do something small? Do something like some people?
Yeah.
Okay. We'll do force of gravity between these. Woo! There we go. Okay, so what do we need to know?
Our weight.
Your weight. Nope, there you go, your mass. Because if we talk about weight, that is the force of gravity. What's your weight?
I'm 145.
You're 145 what?
Pounds.
Pounds. Pounds measures a force. Okay? Pounds measures that force of gravity, it's a weight. What is mass? If we were going to measure mass, what would mass be?
Oh,
There you go, kilograms. If you go to the moon, you'll have a different weight. You'll have a different force of gravity. But If you get your mass, it will stay the same because you still got the same amount of stuff. Okay. So 145 pounds, you know how many kilograms that is? No idea. Do you want to do the conversion or shall I just give it to you?
Just give it to us.
Just give it to me. Okay, that's fine. Because I know I'm about 136 pounds, which puts me at about 63, 64 kilograms. So we're going to call this one 67 kilograms. How about you? 155. Oh, you're huge. So you're probably about, let's just call it 70. Shall we do that? What was that? Were you making fun of tiny people?
No.
Yeah, whatever, man. Okay.
I was here.
So let's say we have a 67 kilogram person and a 70 kilogram person. We want to know what's the force of gravity. If they are, what's the other thing we need?
How far away they
How
are?
about how far apart are they?
Like 2 feet.
No. We can't have it in feet, can we? We need it in
1 meter.
meters. We got to have it in meters. So
1 meter.
1 meter. Let's make it easy. We'll call it 1 meter. That's fine. 1 meter. Okay. So that's how far apart we are. So we have these two people. Well, let's draw it out so we see what's going on.
So cute.
They have. Don't make fun of my drawing.
Can you give me some cool hair?
Give you some cool. Which one are you? You want to be this one?
Oh, yes.
I'm a dog. Literally
There you
chick
go.
nine.
Give it a hat for you. There you go. Okay. So 1 meter apart. One is 67. Oh, wait, that's the wrong one. Here's you. This is Carter. That's 67 kilograms. And this is Owen, and he's 70 kilograms. And we want to know what's that gravitational force between. Okay? So all we got to do, we've got everything we need. We just got to put it in, right? That's it. So I'm going to just rewrite it so we've got it here. G, M1, M2, over R squared. So what was G? 6.67 times 10 to the
Negative 11.
-11th. If you remember, it was newtons times kilograms squared over meter squared for all the units. That's just to remind us, everything needs to be in kilograms, everything needs to be in meters. Okay? And then we had 67 kilograms and 70 kilograms all over 1 meter. And don't forget, that's, whoops, did the wrong one. Don't erase it. That square, oh, let's not use that one. That makes the same problem. Let's use that. Don't forget that square. That's the most popular mistake to make when we do the calculations. Forget the square. In this one, it won't make that big of a deal because it's 1, right? But if we change that from a 1, then it's going to make a big deal for us. So make sure you remember that square. So calculators then. We need to do the top. 6.67 times 10 to the negative 11 times 67 times 70. Tell us what that is. I'll do the bottom for us.
TI 92.
3.128, what?
10 to the negative 7.
Times 10 to the negative 7. And our kilograms are going away. That's going to leave a newton over a meter squared. That's going to get rid of meter squared. That's going to come out in units of newtons. And newtons is what we measure force in the metric system. It's like pounds, but in the metric system. Okay? Did we confirm it? 3.128 times 10 to the negative 7? Yes, we did. Okay. So then we just divide that by 1. I can do that one. I'll do that one for you. I know I'm very generous. I'm saying I never do anything for you. So it's 3.128 times 10 to the negative 7 newtons. So what's a newton? Well, how big or small is that? That's pretty small, and you're just guessing because it's to the negative 7, right? So that's 1 kilogram. Okay? That is 9.8 newtons. So about 10 newtons right there. Feel it? There's 10
Whoa.
newtons. That's
Actually
10
heavier than I thought.
newtons of weight that we've got right there.
It's
Okay.
Oh. I was like, oh my god. This
So
is
if that
heavier than
kilogram is 10, is about
I'm
10.
only 145.
And this is 1, 2, 3, 4, 5, 6, 3
Do
newtons.
you guys want to? Don't drop it.
So
It's
that's
kind
like-
of. It's heavier than you think.
Wait, so
It
this
is
number is
heavier.
kind of like a third of this?
Not even a third, is it?
Like
So
almost
this is
a third?
10 newtons, right?
That's
Right.
1
A
kilogram.
third of it would be like
Oh,
3 1/3 newtons, right? So this is point
Oh.
6 zeros, 6 zeros,
So
no,
it's
1,
like
2,
300.
3, 4, 5, 6, 3 newtons, right? That's it. So this is like, there's tenths, hundredths, thousandths, 10,000ths, 100,000ths, so that's it. So this is actually 31.28 times 10 to the negative 6. Negative 6 is micro or millions, right? So this is 31 millionths of a newton.
Whoa.
So it's pretty small, right? That's the idea. It's really tiny. We can give you an even better number. Somebody take that number for us and multiply it by 4.45. So if you take 3.128 times 10 to the negative 7th, you multiply it by 4.45, you get pounds, a number you're more familiar with. So that would be the equivalent of 0.1, 2, 3, 4, 5, 14 pounds of force.
Oh, I got you.
So pretty small, right? That's why you can walk by people. You don't. It's not like you walk by and all of a sudden, whoa, gravity's pulling me in. Okay.
Mine.
There, that's,
I
you're
do
so
that.
massive. That's it.
Sorry, gravity
That's
just
it.
pulled me towards
It's not like gravity pulling you in,
Only girls though.
right? Okay. That's why we say gravity takes a huge mass in order to do this. In order to feel it, you got to have an object like the size of the Earth for you and I to feel it. Or like the moon. The moon's pretty small compared to the Earth. And we still have gravity, but you can see from the videos that they walk kind of funny, right? Because gravity is different, because it's smaller. on them. There, you could jump a lot higher, right? You can jump a lot higher.
Wait, so to go from James to Anne, you always do it by what's like
Yeah, but don't worry about that. You won't have to do that. That's what I pulled out. I just have that memorized for the physics stuff. You don't have to worry about it. Okay? If you were ever going to have to do that, I'd like to give that to you.
Wow.
So there's our calculation. Woo, that hard?
Not really.
That seems pretty easy, but what else could I ask? Let's go, we'll go new page. Let's look at our formula. Whoops, G, M1, M2 over R squared. We asked, what's the force, right? What else could I ask using this formula? I could ask for a radius or a distance between two objects. I could give you a force, give you some masses, and find out how far apart they are, right? What else? I can ask you for either one of the masses, right? This is how we weigh planets and stars. Because what we can do is using other measurements, we can get the gravitational force. And we can measure how far away we are. And so then we can come back here and we can calculate, like if M2, maybe that's the mass of a star or the sun. And we can then calculate how big a star is based on that gravitational force.
Is the gravitational constant?
It's everywhere in the universe. It's a constant in all of the universe. So it's always the same number. It doesn't change because we're in a different place. Yep. Okay. Making sense? Okay. Or at least we think until we maybe try some problems. Looking for a mass or a distance? Which one shall we do?
How about this?
You want to do a distance? Okay, let's do a distance. What do we want to find the distance between? Let's pick some planets.
Mars and Earth.
Mars and Earth. So we have
is
Mars
blue, it's red.
and we have Earth,
Isn't
right?
sugar red?
Let's see.
Is it orange?
We're going to be able to do Mars and Earth?
We can do Mars and Pluto.
Well, the trick is, now remember, that's what I'm thinking about. Here's our formula, right?
Sorry.
Cheers.
This is our formula, right? So if we're gonna find the distance between Mars and Earth, we need to know what? We need to know the mass of each one, and
The force.
no, we're looking for the radius, aren't we? Because that's what we want to know.
Wait, when we have to switch the formula around now?
We will, but let's look at it. See, this is what. So we need the masses. What else do we
The
need?
force.
We need the force. The force of what?
Gravity.
Between
Mars and Earth.
Mars and Earth. So let's do this before we go further. Let's see if we can find it. That's something I don't know off the top of my head. Let's look it up. We need the force of gravity between Mars and the Earth. Go. Let's look it up and see if we can find it.
What is the force of gravity between Mars and Earth?
Force of gravity between Mars and the Earth was what?
8.7 times 10 to the 60 joules.
Okay. Let's go with that one and we'll see if it works out. Okay, so we also need, you said we needed the mass of the Earth and the mass of Mars, right? Who's got it?
Mass of Earth.
Yeah, Joseph?
The mass of Earth is 6.0 times 10 to the 24th kilograms.
They rounded that one. Okay. We got the mass of Mars. Should Mars be bigger or smaller than the Earth?
Probably even bigger. No, smaller.
There you go, Mars is smaller.
I get it.
It's close. Got it?
6.39 times 10 to the 23rd kilograms.
No.
Mass.
Okay,
Martians.
so we'll go here back to our formula. 23rd.
Everyone's
Okay, what are we going to do? We need to solve this. We need to solve it for R, right? So what are we going to do first? What should we do first?
You need to fix the formula.
Okay, how are we going to,
You divide by force of gravity and then times by radius.
okay, so which one, we're going to do one step at a time. So which one are we going to do first? Which one do you want?
Radius.
The force of gravity, divide by the force of gravity, or multiply by radius? Do the radius first. Okay? I like that because most people don't like fractions, right?
I hate
So if we do that first, it gets rid of the fraction, right?
it.
So we have r squared times f sub g equals g m sub 1, g m sub 2. Now we divide both sides by the force of gravity. That moves gravity to the other side, that force of gravity, and it says r squared equals g m1 m2 over f sub g. What do we need to do now? We need to take the square root, right? So we square root both sides, and that says r equals the square root of g m1 m2 over f sub g.
Huh.
Okay with that?
Alright.
Nice little algebra there, right?
It's always good preparation for the math class.
There you go. So then r equals, we're going the square root of 6.67 times 10 to the negative 11 times, what was the mass of 1? Which one is 1 going to be? Is 1 going to be
Earth.
Earth or Mars? Is it going to be Earth?
Earth, 'cause
So
Earth is
I'm going to come back here. I'm going to make that one Earth. I'm going to make that one Mars now instead of 1 and 2. Is that okay? Okay. So mass of Earth was 6.0 times 10 to the what? 24th? What's up? What do you got? You got a question or did you get an answer? Okay. And the mass of Mars was
6.39 times 10 to the
23rd. All right. All over. What was the force of gravity between the Earth and Mars? Remember? Neither do I.
8.0
8.7 times 10 to the 16. And those are in kilograms. The two masses are in kilograms. And the force is in newtons. So that lines up with all those units on that G, right? Everything we need.
Oh,
So R equals the square root of, shall we do all the top?
those are the
6.67 times 10 to the negative 11 times 6 times 10 to the 24th times
Wait,
6.3 times 10 to the 25th.
oh, you don't add the math again?
No, because it's with the parentheses, these are multiplications, right?
Gotcha, okay.
So we're multiplying those numbers.
Oh, I was getting mixed up with the last equation.
Okay, what do we got?
2.5573 times
10
10 to the 38.
to the 38. Okay. Over 8.7 times 10 to the 16th. So now we gotta divide them, right? Let's divide those two numbers. 2.5573 times 10 to the 38 divided by 8.7 times 10 to the 16th. What do we got? 394 times 10 to the 21st. And square root that. What we got? Where'd you get?
It's like 5, 4, 2, 1, 6, 2, 3, 3, 7, 2,
Whoa, that's way too fast. 5, 4, 2, 1.
6, 2, 3, 3, 7, 3, 1.
Do we need the point? We're talking distance between Earth and Mars. Is the decimal point going to make a big
No.
difference? Nah, we're okay. Well, we'll leave that one out.
Not right then.
I don't know. That would be the same as, let's look at this for a second. That would be 5.4
That's what I got.
times 10 to the what? There's 3, 6, 9, 10. To the 10th, right?
That's what
So that makes sense with this number to the 21st. We square root that, then we get something smaller. Is that what we got? So we have confirmation. So that looks like what we got. What units?
Newtons.
No, because this is distance. What was that?
Meters.
Meters. So it would be, what is that? Let's see, this is million, right? This is billion, so 5.4 billion meters. So let's look it up. Let's see if we got used our right gravity. Let's check and see. What's the distance between Earth and Mars?
5.5 times 10 to the 10.
Whoa!
Ooh, so close.
That's what we get when we look it up. That's pretty doggone good for looking all this up, right? And because everything was rounded a little bit, remember? Because that's the other thing. Now think about this. There's the sun, there's the Earth, there's Mars. Is that the way it always is? These two stay in a line all the time? No. Because we could have it even, come like this. We could have Mars over here and Earth over here, right? Or we could have them lined up, or we could have them any other position. And now we've drawn it not quite right because really, it's like this, isn't it?
Yeah.
So we could have times when maybe they're closer together depending on when they're in orbit and they're further away. So we take kind of an average of all of them. That's what we've got. Okay?
Do you,
So that's
Like,
it.
stop